Okay, I'm going to try to make a quick video. Again, I'm trying to keep these things under 15 minutes if at all possible. Please watch and take notes. Like I said, this is our trade-off in order to take advantage of some class time to do some fun activities. So I just want to tie together something I mentioned very briefly this morning in class. We talked about how to calculate absolute pressure. And absolute pressure, the other name for that is total pressure. If we pick some point in a system, say the elevation A, some depth A, and notice that this is open to the atmosphere, and we'll talk more about this in a second. Then we have the contribution to this total pressure, or absolute pressure, is the atmospheric pressure plus the pressure due to the weight of the water. So we have the pressure due to the weight of the air, PO, and the pressure due to the weight of the water, rho GH. And again, that's a simple calculation. There are occasions where, and again, this is something that I generally don't care about, but the AP does. Where we talk about something in a gauge system. I'll give you an example in just a second, a more pertinent example. But when you have gauge pressure, the system itself is not open to the environment. So again, if you get your blood pressure taken to a doctor's office, your veins hopefully are not open to the environment. So we simply say it's the absolute pressure minus the PO, or you can just say it's rho GH. So if I go a certain depth inside a pipe or container, I'll show you an example of that. The reason why this example that's important is it lays the foundation for something called Pascal's principle. And that's what you're using with your hydraulic arm. So I want to show you a couple things here. So first of all, again, if we look at this here, some scuba divers down at the bottom or someplace in the ocean, we have the weight of the water and we have the atmosphere. So they're open to the atmosphere, so they feel the pressure due to the water, but also the atmosphere. It's an open system. There are systems like your robotic arm that are not open to the atmosphere. So the fluid, the water in those tubes, is being acted upon by your syringe. You push the syringe, that pressure and that force is transmitted through the tubes and it comes out the other side. And the tube is a fixed diameter. The entire length of the tube is the same diameter. The syringes are the same size. That will be important in a second. Also in your home, for example, you may not know this, but in your home you have a heating system. You have some sort of hot water probably running through your house, not only for your tap, but also for your heating. And that's a closed system. They put water in the lines of your radiators, and that water is the same water that keeps on moving around that radiator. It gets heated, goes to the radiator, cools off, comes back, gets reheated. So that's a closed system. It's not open to the environment. The taps in your house are not open to the environment until you open the tap. And so again, your syringe and your robot is doing the same thing. Now, this brings up Pascal's principle, and I would like you to write this down. You probably have seen Pascal from math class. I'm sure they've talked about Pascal. He did a bunch of math stuff. He stated the following. He said, the pressure, and be careful, not the force, but the pressure applied to an enclosed fluid, this is a fluid enclosed, not open to the atmosphere, that pressure is transmitted undiminished to every point in the fluid. So the pressure is transmitted undiminished to every point in the fluid. And we'll take a look at what that means, or how we apply that. So it says the pressure everywhere is constant, and as soon as it's motionless and it's at minimal depth. And I'll explain what that means a little bit later. So for example, when you grab a balloon and fill it full of water, if you squeeze the balloon, we don't compress the water. And again, this is important. It's a consequence of the fact that liquids are incompressible. The volume stays the same. So all you do is you're moving the water around, or the balloon explodes. So the pressure stays the same within that system. Okay, and this will make sense in just a second. So again, pressure applied to an enclosed fluid is transmitted undiminished. The pressure is transmitted undiminished to every point in the fluid. Well, what's that mean? And I'll try to shoot a video and show you this as well, or I'll show it to you in class. But here is the simplest application. It's called a hydraulic lift. So when I take my car into the shop to be worked on, or I jack up my car, or something like that, or even your robot arms, it's taking advantage of this hydraulic system, this Pascal's principle. So here we have a piston inside a cylinder. It's like a piston that you're using in your robot. This has a certain diameter, certain area on the input side. So we're going to apply a force on the piston to push it down. And this fluid, usually water or oil, is going to transmit this force and this pressure to the other side. So I push down here and it lifts a load on the other side. So here's the input side. You input a force and the piston moves down, but this piston has to move up and the load is lifted. Now the key here is that the size of this diameter on the input side and the size of the diameter on the output side are the same, and that's what your robotic arm does. The pistons are the same size, The syringes are the same size, so you push on this end and the arm moves on the other side. Force in, force out. Okay, now that's a simple system. It doesn't really have an advantage other than to transmit this pressure, this energy. Now here's one of the simplest questions. It's kind of the same idea. Now we're going to put a little math to it. So I'm going to apply a force, let's say 100 pounds. I'm going to do that on a piston that has an area of 10 square inches. And remember, pressure is force over area. So I have a force of 100. I have an area of 10. Well, it sounds like 100 divided by 10 is 10. But the pressure, Pascal's principle says the pressure is undiminished. That means the pressure stays constant. So the pressure here is 100 divided by 10. So it's 10, and it's 10, and it's 10, and it's 10. And it's 10 everywhere. We're assuming that this is minimal depth. So it's 10 here, it's 10 here, it's 10 here. We're not worrying about the weight of the fluid inside this closed system. So here's the simplest question in the world. If the area stays 10 and the area stays 10, and I apply 100 over here, well, what do I get over here? Well, of course, I get 100 out the other side. So if I put 100 in, I get 100 out. And that's kind of obvious. Now, that doesn't really give us a great advantage. In other words, there's no what we call mechanical advantage. We're getting out exactly what we put in. So you might ask, what's the point of it? Well, how can I improve upon this and use Pascal's principle to, for example, lift something heavy? If I put a piano here, I'd have to push down with a force equal to the weight of the piano to get the lift. Well, take a second to think about how I might improve the system to be able to lift a piano with my pinky or with my foot. My car, for example, gets lifted at the shop. When they take my car into the shop, they put it on a lift, and they hit a button, and my car goes up. My car weighs 4,000 pounds. They do not apply a 4,000-pound force. They apply much, much less force. So if you haven't figured it out, the easy way of doing it is the following. You simply, let me get my pen working here. You simply have an input side and an output side, and the trick is to make the input side tiny and make the output side larger. So because the pressure equals the pressure, the force per area equals the force per area. So because the pressure is a constant, this would be like 3 over 3, and this would be like 100 over 100. It's still 1. The pressure stays the same. So if I make the area larger, I get a bigger force. And it seems to violate common sense. You might say, well, I'm getting something for free, and we'll talk about that in a second. So I could literally put a car over here on this side, and I could put a tiny force in. But I put a tiny force on a tiny area, and I seem to get a huge force on a huge area. Well, although it seems like it violates some rule, it turns out this is exactly what happens. So you can lift a car with your pinky. You just have to have the right system with a fluid in here to transmit this pressure undiminished. Now, again, the classic example is a car, and my face is in the way here, but I'll shrink that down a little bit. Here's a picture, and every textbook has this, and when I eventually give you a textbook, this is something you might want to jot down. You can freeze the video and take copy it in or take a picture of it and embed it wherever your notes are, but it's basically the same idea. I'm going to have a small area, area 1, and apply a force F1, and if I make the area 2 really large, F2 becomes really large. And again, the pressure is constant, so the ratio of F to A and F to A is constant, but if I change the area, I change the force. And it seems to be something for free. It seems to be if I put a small force in, I get a big force out. That shouldn't violate conservation of something. So if you think about it, take a second to think about this, and just kind of give way in the picture. What's the trade-off? And if you think about it, there's no law of conservation of force, but there is conservation of energy. And obviously you heard that last year, but conservation of energy is also conservation of work. Remember the work energy theorem. When I do work, I give something energy. So when I do work, when I apply a force over a distance, so here's my force being applied over some distance. Well, the product of these things, the work being done, has to be conserved. The work in and the work out has to be the same. So the force times the displacement equals the force times the displacement. Delta X. So if you look here, if I make this force small, then I get a big force out on this side. then the distance this thing had to be much greater, and the distance I get it to move is really small. So it's basically this: I'm going to have a tiny force, but a huge displacement. And on the other side, I'm going to get a huge force, but it's only going to move a tiny distance. So this is a little messy, but you get the idea. There's no conservation of lifting. There's a conservation of energy or a conservation of work. The product of F times X, work, has to be conserved. So I have to move this. I have to apply this force over a huge distance to get this giant force out over a small distance. And I'll show you something in class. I actually I'll try to shoot a video of this a little bit later, or I'll show you in class when we come in on Friday. I can lift a stack of books. I have a little mini hydraulic lift, and I can lift a stack of books, but I have to push the syringe like 5 inches to make the books lift a 1/4 inch. So again, keeping that in mind. I'll do an example. You might want to copy this into your notes. Kids often say that we need to see lots of examples. Again, the AP is much less about calculating stuff, but a lot of kids like to have notes with examples done, and that's a good idea. So you might want to stop the video, plug in these numbers, make sure everything's been converted to proper units. I think I have areas and forces, and you can figure out what something can lift. So again, do this, and we'll talk about it in class at some point. Here's a kind of a mini tipper. And again, same thing. I'll try to do this in class also, but you might want to stop the video, and you're ranking these forces, F1, F2, and F3 in these 3 scenarios. So you can do a ranking task. Remember in ranking tasks, I don't know if Mr. Horgan did it, but I have the kids circle. So for example, I'm just making this up. If I said F1 was equal to F2 is bigger than F3, you could do it that way. What I normally do to kids is I say circle things that are equal. Sometimes that equal sign is tough to read, so I prefer if you circle things that are equal. So again, stop the video, take a look at that. You may want to draw it in your notes, and then come up with an answer and talk to your friends, and we'll discuss it very briefly in class when we get back. I really want to use our Friday time to do the robotic arms. So Pascal's principle has some great applications, and in real life, again, the whole point behind engineering is taking physics theory and applying it to something useful. Now, you probably drive to school, or at least ride in a vehicle to school, either with parents, a friend, or a school bus. And a great example of this is a braking system. So if you ever watch the Flintstones on TV, Fred Flintstone gets the car moving, and he uses his feet to stop the car. It's very ineffective and probably pretty dangerous. Instead, to stop my 4,000-pound car, I use a fluid in the braking system. It's a closed system, like your syringe, and it is made up of a brake pedal. You push the pedal and the magic happens. But what's really happening? Well, there's a fluid. When you press this brake, you're actually pushing a syringe that's pushing fluid through a bunch of brake lines. So in your car, you push on the brake and it pushes fluid to the front right, the front left, the back right, and the back left. They've shown 2 different types of brakes. It used to be some cars had disc brakes, and usually in the back of the car they had drum brakes. Very few vehicles use drum now. Almost all cars have disc brakes on all 4 wheels. And a disc brake is just like your bicycle. Basically what happens is that when you brake your bicycle, you pull the lever and it makes these things clamp on the wheel. So here's a wheel spinning kind of away from you, and there's one side and the other side. And when you push the brake pedal, it compresses the piston and squeezes a pad against the rotating wheel, and it stops the brakes. So stopping your car is what we call power brakes. Your car has power brakes. You put a tiny force. You don't have to stomp on the brake. You put a tiny force on the brake pedal, and it exerts a huge force on the disc. That's because they change the ratio of the area to the force to the force. So they get a huge force out by making the area larger, tiny force in by making the area small. And again, there's a million applications of this in real life. If you look at any of these big machines, they lift up these big buckets. These are all hydraulic systems. The pistons are here full of oil. These are pistons full of oil. Even airplanes steer by this. I usually tell the class a story about an airplane that had the cables, the hydraulic cables snapped. They were actually engine exploded and actually cut the hydraulic cables. And the pilot was able to fly the plane and land it. Unfortunately, some people died, but the fact the plane was able to be flown for like 100 miles and landed near an airport, not exactly on the runway. He was actually able to use the engines to steer left and right and up and down, even though he had no steering from the flaps. He wasn't able to control the hydraulic flaps. But hydraulics is everywhere. It's a super useful application of Pascal's principle that the pressure stays constant and we just change the ratio of the areas to make it work. And again, that's what you're doing. Now you're not changing the area. So you push into a force of 10, you're getting a force of 10 out because these syringes are the same size. Everything's constant. But again, this is a great application. I will, when we come back to class, we're going to do the contest, and I'll probably very briefly show you a video clip or two and do a demonstration and may even do a calculation or two. And I eventually will assign a homework. Like I said, this is a new process this year, trying to take advantage of flipped notes so that we can do interesting stuff. And I'll try to have better versions of this, but this is a trial for the day. Okay, so that was the attempt. Let me see if I can stop this thing. Okay.